If you're building a TypeScript AI agent for production, you need to hear this first. Too many agents are being shipped to production with wide open endpoints, no cost guardrails, no tenant isolation, and little to no real observability. I'm going to show you 5 best practices that fix exactly these problems. When your agent calls tools, the response can take 5, 10, 15 seconds. If you just wait for the final answer and dump it all at once, the user is staring at a spinner the whole time, and that's not really a great experience. The best practice is to stream 3 types of events back to your front end. First, the text deltas for the token by token typing effect. Tools start so the UI can show looking up your orders, and a tool end when it finishes. That way the user sees activity the entire time, even during a 10-second tool call. Here's how that looks with Strands. You call agent.stream, iterate over the events, and send them as server sent events. Notice we pass invocation state here. That's how the authenticated user ID reaches the tools without the model ever seeing it. The tool events are what makes the difference for your users. Instead of seeing a blank screen for 10 seconds, they see a using tool, get user orders, and then the text starts streaming in. It feels responsive even when the agent is doing heavy work behind the scenes. Streaming, tool events, all working. But right now, this is just an express server on localhost. Anyone with the URL can hit it. And there's no auth, no rate limiting. That's what we need to fix next. For production, you want your agent running as its own service. That way you can put a gateway in front with credentials, scale it independently from your front end, and deploy it to something like Agent Core that requires its own container. I'm using AWS for this, so I'll show these specific services. But if you're using a different provider, the same pattern applies. Gateway in front that handles auth and rate limiting, compute in the middle, agent behind it where users can't hit it directly. I deployed this to Agent Core runtime on AWS, but the same pattern works on ECS, Lambda, or any other container platform. What matters is what you put in front of it. API Gateway with a Cognito authorizer handles Auth. We attach AWS WAF in front of it for 2 things: a managed rule that blocks common web attacks like SQL injection and cross-site scripting, and a rate-based rule that limits requests per IP. Then a Lambda function sits between API Gateway and the agent to bridge the auth. You might be tempted to configure your agent runtime with OAuth so your front end can call it directly. But if your gateway and your agent accept the same tokens from the same identity provider, a user who finds the agent endpoint can skip the gateway entirely. All your rate limiting and filtering gets bypassed. A better approach is to leave the agent on IAM Auth, which is the default for Agent Core. Then put a Lambda between your gateway and the agent. The Lambda has an IAM role with permissions to invoke the agent. Your users authenticate at the gateway with OAuth. The Lambda extracts their identity with JWT and calls the agent using IAM credentials. Now the agent endpoint is only callable by AWS services with the right IAM role. Users can't reach it directly even if they find the URL. You'll notice user ID is in the payload here. The container receives it and maps it into invocation state server-side before the agent ever runs. The model never sees it directly. That's the same isolation we set up in section 1, just crossing the service boundary. If you're running your agent on ECS or Lambda instead of Agent Core, the same pattern works. Put a gateway in front and use service credentials on the internal call. On the front end side, your TypeScript app just swaps the URL. Instead of calling the agent directly, it calls API Gateway with the user's Cognito token. Same fetch, same SSE parsing from section 1. The front end doesn't know or care that these are 3 services between it and the agent. Right now, our tools return hard-coded data. We need a real database, and this is where I see a common anti-pattern. A lot of demos give the agent a tool that takes raw SQL. The agent writes the query, the tool runs it, and it works. For an internal analytics tool, that can be fine. But for customer-facing agents with multi-tenant data, it's a different story. In production, the agent could write a query that pulls another user's data, or a delete statement, or select star from a table with millions of rows. Instead, define a specific query shapes as type tools. The agent decides what to look up. The tool controls how the query runs. Look at this. Status is an enum, so the agent can only filter by pending, shipped, or delivered. The limit maxes out at 50, so no runaway queries pulling a million rows. The user ID comes from invocation state, which the request handler sets from the verified JWT. The model never sees it. It can't be tricked into querying another user's data because it doesn't even know the user ID exists. And the query itself is parameterized, so no SQL injection either. This is called a contracted surface, pre-authorized query shapes with observable side effects. The agent reasons about what to query, the tool controls how. And that's it. The agent gets back real order data, but only for the user who's logged in. It never sees another user's records because it never controls the user ID. Okay, so at this point, we've got a deployed agent, it's authenticated, it's talking to a real database. But there's nothing stopping it from looping. If the agent gets confused on a request, it can call the same tool over and over and burn through tokens until the request times out. So you need guardrails. So I added 3 things that I now put on every agent I build. First, lifecycle hooks. Strands has an add hook method that lets you intercept the agent loop. You pass it in an event type and a callback. Before tool call event fires before every tool execution. So you can inspect what's about to happen and block it if you need to. If you set event.cancel to a string, that string becomes the error the LLM sees, so the agent can respond to the user gracefully instead of silently failing. The hook does 2 things. First, it blocks any tool whose name starts with a destructive prefix like delete, drop, or purge. Second, it keeps a counter. If the agent has made more than 20 tool calls in a single request, it cuts it off. Without that, a confused agent can loop forever. Add hook returns a cleanup function. Same pattern as React's useEffect. In this setup, each request creates its own agent instance, so the hook and the counter are both request scoped. If you're using a single agent across requests, you need to handle that differently. Second, timeouts. Call agent.cancel after a deadline. If the agent is still running after 25 seconds, kill it. Third, model routing for cost. Not every message needs your most expensive model. Simple questions like, what's my order status, don't need Sonnet. You can route those to something like Amazon Nova Micro, which is cheaper. The is-simple query check can be as simple as message length and keyword matching, or you can use a cheap classifier call. Nova Micro supports tool calling through the Converse API, so it works with the same type tools we set up in the last section. The gap between a lightweight model like Nova Micro and Sonnet is significant enough that routing even a portion of your traffic saves real money at scale. Last piece, when a request takes 8 seconds, you need to know if it was the model thinking, a slow tool, or too many reasoning cycles. That distinction changes whether you fix the prompt, optimize a tool, or add a cycle budget. The good news is with Strands, every time the agent finishes a request, you get metrics back automatically. No collector needed and no extra setup. Cycle count tells you how many reasoning loops the agent went through. Total duration tells you how long the whole thing took. Token usage gives you input and output tokens so you can track cost per request. And per tool stats show you which tools were called, how many times, and how long each one took. In our streaming setup from section 1, these come through in the agent result event at the end of the stream. We already sent them to the front end with our done event, so you can show response times and token usage right in the chat UI. So you want to log these on the server side. High cycle count with repeated tool calls means the agent is looping. High duration with 1 cycle means the model is slow. Now you know where to look. For the full distributed trace in production, setup tracer instruments everything with OpenTelemetry spans. Let me show you what this looks like in the console. If I set trace console 1 and send a request, you can see every span in the terminal. Agent invoke, model calls, tool execution, all nested and timed. In production, instead of logging to the console, these traces go to your OTLP endpoint. CloudWatch supports direct OTLP ingestion now, or you can point them at Langfuse, Datadog, whatever speaks OTLP. It's standard OpenTelemetry, so you're not locked in. So those are the 5 best practices. Stream with tool call event so your UI stays responsive. Separate your auth layers, OAuth public, IAM internal. Use contracted database services with tenant isolation. Set guardrails and budgets so your agents can't run away. And use the built-in metrics and tracing to know exactly what your agent did on every request. None of this is required changing the agent's core logic. It's the same TypeScript, same Strands SDK, same tools. We just kept adding production layers around it. And if you want me to go deeper on any of these, just tell me in the comments and subscribe if you want more content like this.